Hi, this is Dr. Liu. This is the data analysis for thin lenses. And in this lab, we had a number of different methods to measure the focal lengths of these lenses, including converging lenses and finally some divergent lenses. So you're supposed to have two converging lenses and at least measure one divergent lens. You don't have to have two divergent lenses. Some groups did not. There's only one divergent lens they had. So let's go through the procedures. So first, for converging lenses, we can use a parallel rays. This is where we have the light source at one end as far as possible, and then we have the screen at 100 centimeters. So here, two lenses and the screen is at 100 because we need to read the position between the screen and the lens. So the screen has to be at a readable position instead of being pushed all the way to the right. And we measured when we see a clear, very small image on the screen, we measured some distance. So the position of the lens is here, X lens. This is X the other lens. So this would be the one that has a green tint to it. This is the one that is more clear and also thicker in the middle. So that would be the first lens. So the focal length will be just the difference between the two, and you just subtract the two, and you get focal length. You don't have to organize data like the way I did, but at least you should present, for instance, what is the method of measurement? What are the focal length calculations? And some raw data, for instance, at least these need to be mentioned. Uh, Okay. And apparently 50 centimeters to the screen is not very far. 50 centimeters to the light source is also not infinitely far. So this is a very crude method for a long focal length lens like the second one. The first one seems to be okay, but still not ideal. Okay, so moving on to the next method, we're using a telescope. So we use a telescope to focus at infinity or a very far object, see all the way down the hallway, or if you see a window, you look out the window, find a faraway object to focus on that. So then you bring it in and you set up your system. Okay, so this is basically I should probably say where the object is. The object is set at 0. So let me create that just for formality. Object is at 0. And I have the lens in front of the object, and I look toward the lens at the object until I get a focus image. I move the lens, right? So the distance between the object and the lens will be the focal length. This is a better method to get focal length because we're using a telescope which can focus light to well, more or less simulate uh, infinity. So this is a much better method than the first method. And as you can see, the numbers, right? So I'll even do a calculation. You don't have to, but feel like this is a more complete way to show that you have a lens in front of this object, and you can see the image clearly through the telescope, which means the image is supposed to be at infinity. So that would be the focal distance. So there you go, F. So then comes the an even better method, the parallax method, or we call it sometimes the auto-collimation method because the light collimate itself. So this is how I set it up. You don't have to, but you have to have the position of the lens and the position of the object. So you have the little metal hook in front of the lens, and you have a mirror right behind the lens. You move the metal hook back and forth until you see its image, and you move your head sideways. You see the image and the object. They move at the same rate. So that's where you stop. So here it is. This is, in my opinion, a very good decision to basically track the two objects, you can very easily compare whether they're moving relatively, even with a very small amount. And this is what we're good for with our eyes. So lens position, object in front of the lens, subtract the two, that's a focal length. So we have these two. Um, this probably is better off being moved a bit further down to the right in order to make it look like it's a separate method. Okay, I can also uh, resize some of these. Okay, well, it wants to get a little wider. This can get narrower. Okay, all right. So that's for parallax. I would trust these numbers much better than those numbers, and maybe trust these two numbers similarly, but I like this number. This is a much better argument because in the first two, you're both trying to focus, right? Get an image to focus. There's quite a bit of range where you can call it focused. And that also works the same for conjugate foci. This is where you have the object and image with fixed distance, and then you move your lens. When you move it to one position, you have a magnified image. You focus that, so that's where the lens is. And then you move it toward the screen, you see a minified image. This is where your lens is. So the distance between these two is called A. So there you go, distance. And the distance between the screen and the object, which does not change, is this. And then you do a calculation based on the formula. The formula is b squared minus a squared over 4b. It's an unnumbered formula on page 32. So here it is. It's calculated. So if I were to read the accuracy, at least my perceived accuracy, this method is most accurate. This is, I would say, second most accurate, but it has a caveat. Um, you have to be able to have a distance over 4 times the focal length. See this right here? Over 4 times of that is beyond our 1 meter optical light rail. And actually, even more than 4 times is not enough. You need a bit more than 4 times. So we're not able to do that measurement simply because our optical light rail is not long enough. And see this, we can actually still have larger focal length lenses measured because this method is not limited to that, right? So I would say this is better than that and better than this and much better than that. So what kind of conclusion should I draw? I would say that um, I I got the focal length from each measurement. I can list these in my in a small table, or at least mention that one of them is about 12, the other is 25, and then you can refer. You have data tables to show, and this probably doesn't really copy paste into your Word document well enough. So you would rather want this, for instance, um, separate tables like this, and create all borders for the table. You just copy paste this table while including a little title here. Copy paste this one at a time instead of having all these copy pasted uh, together into your Word document. And for this, you can probably rescale, but well, just adjust the width because it shares space with all these other things that take more space. If you copy this to your Word document and try to rescale it on its own, it'll be good enough to just stretch across the entire width of the page. When you're doing something such as a report, you should think about how it prints out. Does it actually look okay when it prints out? If it doesn't, you should make adjustment. You can't just copy paste and not look. So this is what I would do. Just do these separately. Okay. So now after conjugate foci, we're focusing on well diverging lenses. Diverging lenses do not focus. So we have to use a helper, a converging lens. So for this part, you should refer to the schematic diagram where these numbers are like P2, Q2s. Okay. So first of all, we set up an object, we set up a converging lens. These two do not move. So object at 0, converging lens is at 16.3. This is just my setup. Yours could be different. And then I find the image. So this is what I did. I basically just have these two set up, and I moved the lens to get a clear image. And then I recorded it all three. And then you need to insert your other lens as XL2 position of the lens 2. This is a divergent lens. You need to insert it in between the lens and its image. So I placed it here, and I was adjusting the screen in order to see the image here. And separately, I tried another focal length divergent lens. I think this is probably yeah. I really should have written this down. Which one it is? Is this the one with very thick very thick edges? I suppose this is the one not with very okay. Let me say this. I think this is the one with mm, the shorter focal length. That means a less thick lens, but it minifies more. This one is very thick edge, but it minifies a little less as well. It doesn't really minify as much. So anyway, let's go on and we place a lens. This lens between the first lens and image, move the image, move the screen to get a clear image. Again, this is for getting image, so there's quite a bit of freedom to say, oh, this is focus, or no, that's focus, right? So the uncertainty is very similar to some of these results. And we did the calculation. So the Q1 is not really necessary, but I did mark it. So what is P2? P2 is from the diverging lens to the original image. So that would be the diverging lens right here to the original image, right? So image to the right being positive. So I did a 60 minus, let's see, from, okay, here. Oh, right. I do need a negative because it's to the right of the lens. Okay, I didn't see that on the image. Okay, so I did a negative, basically 44 minus 60. And I also did that same thing for this other lens. Okay, Q2 is measured to the right of the second lens from the second lens position to the image position. So this is easy. Subtract the two, use a positive because the image is a real image, even if it went through a divergent lens. The image is still where we collected the light rays with a screen. So the screen says here, real image shows up on it. Right? So here's Q2. And P 1 over P2 over 1 over Q2 equals 1 over F2. So I can solve for F2. Just solve for it and you get this. So it looks like that's another something like a 12 and 25, 12 and a half, maybe 25, 0.4. So that should be clear enough how you analyze your data. So what I expect from you is just basically the analysis with your numbers. I'd like to do it this way. The left side is the left side object, right? You uh, just enumerate all of the objects, something on the light rail from left to right. This makes you can close your eyes and picture how you place all the elements in there. All right. Thank you.